Morning, everyone. Morning, Shimti. And I was unable to connect. Finally, I have connected. So let us start the class. I think we were with the rectangular tanks. And today I'll do one thing, okay? The class from 1 p.m. that I'm going to take, I'm going to continue with this class. Today I have two classes, right? From 11:15 it was, and then from 1 p.m. So I'll be continuing this class. Okay, the 1 p.m. one at 12, I think. Okay, so I share my screen. I'll share with you all this PDF. Okay, so don't worry. At the end, I'll share this PDF. The entire all the things are there from flat slabs to distress. Everything is there. And then where we have done here. Yeah, thanks. So I did I do with you all this constants, this moment of resistance factor, etc. Did I have we done this? Modular ratio, neutral axis coefficient, lever arm coefficient, then moment of resistance factor Q. Have we? Okay, yes, Nancy. Yeah, thank you. So okay, we have done this. Now, once we have done this, we have calculated this. Now, what we can do is that we have to, since it was satisfying the uh, type 1, that means the first we are going to design it as top continuous frame and the bottom will design it as a cantilever. So here now you see cantilever, now continuous free section. Here in the continuous free section we know what is our water pressure which is acting is, because you see here, I don't know, I'll show you, I'll draw and show you. Wait, constants we have done, right? So now if I show you, if I draw this annotations here, suppose this is your rectangular water tank. Okay, now this portion, this one is your 6 meter given to you. Then we have this one, 3 points. Sorry, how much this was? We had calculated, right? It was given to us 6 meter. Okay, it was 3.7, I guess. Yeah, the total height. Okay, this was your length, and this we are talking about the this one. Okay, this is the height. This is the height which is given to you here. It is how much? 3.7 meter. Here it is 6 meter length, we know, but this is the height. Okay, so height is this much. Now we know, we have calculated that here, okay, this one here, this is a loading for the frame action. Okay, now here you will see again, this one was how much? 3.75. Okay, and we have this portion. This is 1 meter, because this 1 meter we have to design it as a cantilever here, right? So if I mention you here, this is your this is your what? This is your loading for frame action. Okay, this is your loading for frame section. Then we have this one. We have calculated this, right? This is your small h. This is your capital H minus small h. This one is your capital H. Here, if you see, this is your capital H is 3.7 meter. Then we have 3.7 meter. This is your 1 meter, which is to be um, designed as a cantilever. Now this portion is your how much? 2.7. Hmm. Yeah. This one till here. Then we have till here. Okay. This is your 1 meter. This is your 2.7 meter here. This is a loading for the frame action. And now you see here, this was your capital, this one water pressure action above here, the water pressure which are coming here on the your rectangular frame here in the rectangular tank. The water pressures from here is coming on these wall, sorry, this walls, right? So that means what, this water pressure here, it is more here on the upper portion. So that water pressure is how much? Gamma w into h, and this h is, you already know, this capital H minus small h. This is your small h. Small h, sorry, small h is this much. So you have this length is how much? Capital H minus small h, 2.7 meter. Okay, 2.7 meter. Now if I draw here a pencil, suppose this portion, this is your, this is how much? This load is this one. This pressure which is acting is this one. Capital gamma W into this one. Gamma W into H, which is H is this one 2.7, capital H minus small h, and then we have total is 27 kilonewton per meter square. Since it is 28 kilonewton per meter square, so that means this value, this one is your how much? This one, this load is your 27 kilonewton, 27 kilonewton per meter square. Yeah, kilonewton per meter square. This portion is what? This portion is a cantilever action here. I'm sure you here. This one is how much? This is your loading for cantilever action. ION. So this is loading for cantilever action here, this portion, and this is your loading for the frame action, the continuous frame which we are going to use. And here we know how much is the pressure here. From here it is 27 kilonewton per meter square, which is water pressure action is capital H at above capital H minus small h, or you can say at a depth of capital H minus small h. It is how much? P is equal to gamma into h, and your h is this portion capital H minus small h here. So the pressure which is coming here is how much? 27 kilonewton per meter square. Okay, now this one, if you see, it is how much? I have to remove this now, this annotations, because otherwise it is not moving down. Okay, so once I click, it will go all this things whatever I have drawn now here. This is the elevation you can see of the tank. This is I can show you. I'll mention it here. This is your elevation of your water tank, your rectangular water tank. Okay, so you see here all the things here. It is mentioned 27 kilonewton per meter square of your pressure is acting here. Now we shall go behind, and we can go at the bottom, and we can find out the fixed end moments. We have to find out the fixed end moments here now, because you see now this was the elevation, right? Now you see here fixed end moments. If you see now, we have to calculate the fixed end moments here. So um I'll remove this all. Okay, now you see here, this is the fixed end moment here. Now this one fixed end moment, we have to calculate this. You see here the top view here, this is your water tank here, 6 meter. This was short wall was 4 meter. Here you had your longer wall 6 meter. This is your 4 meter, the shorter wall. The water pressures are acting here on the wall. Okay, in this way. Sorry, this is straight. Okay, straight. This water pressures are acting here. 1 minute. Okay, so these are the water pressures here acting here on your this inner walls of your tank here. Okay, this is your A, B, C, and D. A, B, C, D. Now we are going to find out the fixed moments here. You see, we'll find out the fixed moment for A, B, then A, D. Keeping this point, this support A fixed here. Okay, we are going to find out the fixed moment of F, M, this one, FAB. That means A is fixed here and B is movable here due to this water pressure. And your FAD. where your A is fixed and D is moving. So you see here one thing that is given by this thing, just WL square by 12, WL square by 12. What is your W here? This is your W, which you have calculated just now, the pressure which is acting actually. That is how much? 27 kilonewton per meter square. And your length, if this you're if you're assuming that you're considering this A and B fixed moment here, then obviously this length you have to consider. If you're considering this fixed moment here, then you have to consider this 4 meter. Okay, this is 4. Okay, this is 4. So you have got this. Now one more thing. Now you may ask that why this is negative here and here you have positive. There is no minus sign, but here it is positive sign. Fixed moments, right? But then why it is like that? You see here A and B, the fixed moment at A and B, where A is fixed and B is moving. Now you see here when your water pressure is here on the this wall, the longer wall, your B point, we have to find out the B point, how it is moving against this A, keeping this A fixed. So your B, you see here, it is moving in this way due to the pressure, it is moving in the opposite direction, anti-clockwise. And if you see AD, your D, due to this water pressure, it is moving clockwise. So your AD is positive and your AB here, okay. See, the meeting is class is going to end in 5 minutes, but the 1 o'clock class now I'll continue now. Please join in the link of that 1 p.m.'s one. I'll share it once again. After as soon as this class ends, I'll take the attendance also in the second class only. Together, I'm going to take the both the classes attendance, and once this end here, this Cisco WebEx here, the video will be converting. So once it is converted, then after 5 minutes again we'll meet on the same meeting link. I'll share the link. Okay. So once it ends, we'll join in the next meeting after 5 or 10 minutes because I need the video to be converted. Okay. Okay. Now here you see fixed moment here. I said you what? Your FAB, that is a fixed moment, keeping your A here fixed and your B is movable. So your this is moving in how? Anti-clockwise, so therefore it is your this negative, your moment is negative, and you have here this is clockwise, so your moment here FAD is positive. So also when once you have calculated minus 81, you have got the FAB, the moment here, to be minus 81 kilonewton meter, and FAD here, shorter wall, you have got 36 kilonewton meter. Okay. So this was your fixed and moments along this direction, 6 meter length, longer length, that means, and the shorter span, along the longer span and the shorter span. Next we will find out this, since we know now the moment fixed and moment here, we will find out the moment distribution factors. We have to find out why, because we need to find out the moment distribution, we have to do the moment distributions. Okay, and then we have to design the longer wall, shorter wall, etc. So once we know this, so for that we need to find out the moment distribution factor, etc. So once you know your fixed and moments here, you can find out the distribution factors. Okay, I think these things you already have done in your analysis, maybe. Yeah, you have done these things. So moment distribution, etc. Still, since I'll show you, since it is fixed and moment here, we are taking A point fixed and keeping the A point fixed and the others movable. Here we are taking the joint A. So the distribution factor at A will be how much? There are two fixed points, one fixed point A with respect to B, A, B and AD. So AB, A members are how much? This is one member AB, this is one another member AD. This two. Then we have, the stiffness is how much? 4EI by 6. And here also, actually it is, we know the stiffness is 4EI by L. So here obviously this will be 6 because here AB, here your length is 6. And your for the shorter span, you have your length to be 4. Your L is 4 here, 4EI by L. So you got your how much? 0.67 EI for your AB member, For your AD, you got how much? For your AD member, you got it to be 1 EI. This is 1 EI. Okay. So this is for 1 EI. Now the total summation of this stiffness will be how much? This plus this. So obviously it will be 1 plus 0 0.6, 1.6, 1.67 here. So 1.67 EI. This is your I. Okay. So this is the summation of your K value. Now the distribution factor is how much? This is given by K divided by your summation of K. Okay. So K, for AB it is how much? 0.67 EI by this one. 1.67 EI will give you your distribution factor to be 0.4 for the member AB. This divided by this 1 divided by 1.67 will give you your distribution factor for the member AD to be 0.6. So we have calculated the distribution factor for the point for